All right, here we go. So, Chapter 2. Why are we starting with Chapter 2? Chapter 1 is a crash course in calculus. So, if there's stuff that you believe you might be behind on in terms of your calculus education, go back and take a look at some of those Chapter 1 videos that I stole from YouTube. In the meantime, we are going to move along with Chapter 2, motion along a straight line. All right, so the goals here are pretty straightforward. We'll be learning to describe straight line motion in terms of velocity, acceleration, and position. I don't know why I didn't write that there. We will be able to distinguish between average and instantaneous velocity and average and instantaneous acceleration. And by the end of the chapter, you ought to be able to both interpret and draw position time graphs, velocity time graphs, and acceleration time graphs, and be able to use one to get the other. All right? So here we go. So for this chapter, the motion we're going to study is going to be restricted in a few ways. So first of all, we're only going to consider the motion on a straight line, as I said a minute ago. We will really just be focusing on the motion itself, not the forces that cause it. Okay, so this is basically kinematics again. We're going to consider the moving object to be a particle. All right, so when we talk about a particle, we're talking about either a point-like object, like an electron or yeah, cool. Or we'll be talking about an object that moves such that each part travels in the same direction at the same rate, so that there's no rotation, no stretching. So we're not going to be worried about rolling at this point, because that would include rotation. We're going to be talking about objects, either floating through space or maybe sliding across a surface so that the whole object is moving at the same speed. That is the deal. All right, so for this first section, this is really basically going to be however long this video turns out to be, minute review of constant acceleration. All right, so let's start by reviewing the terms we learned last year. So this is going to be super quick. So remember, position is an object's location on a number line. Okay, so we're going to use the letter X to represent position. Remember, you need to identify an origin, and then your position, 1, 2, 3, -1, -2, -3. All right. Distance is how far the object actually travels. So if the object starts here at -3 and then goes to 2 and then back to 0, then the distance would be 5 plus 2, so the distance would be 7 meters there. All right. Displacement is how far your object ends from the starting point. So in that little example I just scribbled on the board, we began at a position of -3, ended at a position of 0, so my displacement there would be +3 meters. Okay? Time is obviously the amount of time that it takes for the change to occur. All right? Average speed is, well, if you don't remember, so we'll write it down. S average is, for a given time interval, it's equal to the distance traveled during that time interval divided by the time it took to travel through that distance. Okay? Average velocity. I'm totally out of room on my board because it's all scribbled on. I promise I'll slow down once we get to some tougher material. So remember, your average velocity is your change in position, i.e. displacement, divided by the time that change took. All right. All right, so speed and velocity. So here's the deal. Some of these guys are vectors, right? So remember, a vector includes direction, right? So I was a little bit sloppy about this last year. Usually when you indicate a vector, you put a little vector hat over the top of the variable, okay? So position is a vector. So technically the symbol for position isn't just an X, it's X with a little vector hat over it, okay? Displacement is change in position, also a vector. All right, average velocity is a vector, right? But remember, speed is not a vector, and it doesn't include direction, okay? So, technically speaking, the symbol for velocity, if you want to talk about the velocity, not average, but the velocity at a given instant, the symbol for velocity is a V with the little vector hat, because it's a vector, right? So this little V with the vector hat means velocity. Okay, it's how fast you're going and the direction, all right? Now, by definition, speed is the magnitude of the velocity. At any given instant, your speed is the same as your velocity, but without the direction. All right, and so for that reason, when we write the symbol for speed, sometimes we'll just use S, it is also acceptable to just use the letter v, but without the vector hat, right? Because the difference between the vector hat and the no vector hat is direction or no direction, okay? So sometimes I will write v equals, and that's an indication of the speed. Whereas if I write v equals with the vector hat, that's talking about velocity, all right? I'm going to try to be much more careful about my vector hats this year than I've been my first couple of years teaching this course, all right? Finally, acceleration. The acceleration at a given instant is a. Again, that's a vector. And then this year, unlike last year, we'll be learning about changing acceleration, so objects that have a non-constant acceleration. And so it'll be important to talk about, me learning how to use a smartboard, it'll be important to talk about average acceleration, which is that. Okay? So all of the ones that have little arrows over the top are vectors. Why we care about that is because we're going to be talking about linear motion. And so anytime a vector points to the right, it's positive. Anytime it points to the left, it's a negative. Similarly, up is positive, down is negative. All right? Now, another difference I guess I should comment on is, you know, last year I pretty much held to this. I pretty much always used up is positive, down is negative, right is positive, down is negative. But there's nothing magical about that, okay? These are just sort of sign conventions that mathematicians use. So occasionally we'll run into problems where, for example, you've got a ball or some object or whatever that's, you know, moving just straight down, okay? Well, so in that situation, if everything is down, then just make down a positive direction, right? If you're never moving up, then it wouldn't make sense to, I mean, you could, but you know, you're just making the work harder on yourself to make everything negative here, right? If everything is moving down, then just call that direction positive. All right? Cool. So here are all of your old equations from last year. These should hopefully all look familiar. All right? You should 100% memorize all of these equations, okay? Oops, except that I need to scroll the page down so you can see them all. There they are. Okay, so you should memorize all of those, okay? Now, a couple quick comments about them. Some of these equations, well, let's see. All right, so what do we got? Also worth discussing speed briefly. We already did that. Check. All right, some of these equations on this list over here can only be used if the acceleration is constant. All right, so let's go ahead and mark those. Let me mark those with, I don't know, how about a green star? All right, so these equations can only be used if the acceleration is constant. So this equation allows you to find the acceleration if the acceleration is constant. If the acceleration is not constant, then that same equation gives us average velocity. And I, again, forgot my vector hats. Okay. All right. Same thing here. These two purple equations here are the same thing. Okay. So if your acceleration is constant, these guys work. If the acceleration is not constant, then you got to replace a with a average. Okay. Let's see. What else? All right. So here were the ones that I was the most worried about. These guys here can only be used if the acceleration is constant. All right? In teaching this my first year, this was a super, super common issue as I had students trying to use one of these last four equations to solve a problem in which the acceleration was not constant. All right? So please, please, please be aware of that. All right? These only work if the acceleration is constant. I know I've said it a bunch. That is because it is super important. All right? All right. Now, when you take your AP test, you're going to be given an equation sheet, a handy-dandy equation sheet, which will give you all of these equations, right? Sort of. So here's the way they look on your equation sheet. All right? So here are the kinematics equations that are given on the equation sheet. All right? The equation sheet is really only there if you get stuck and you forget an equation. These equations you should never forget. All right, you have to know these. All right, so let me take these three equations as they're written on the AP sheet and write them in the notation that you're more familiar with. All right, so all of these x's are just indicating that, oh, we're talking about motion in one dimension. So here, x is that dimension. Okay, So this equation right here is the same as what we learned last year as this. Final velocity is initial velocity plus acceleration times time. All right, so it is not unusual for people to use v to represent the velocity at some time and v naught as the initial velocity. All right, I'll kind of be alternating between the two throughout the year. I really still like this initial and final notation better. Occasionally you'll see this, the velocity at time t is equal to v naught plus acceleration times time. Okay, so that is what this equation is. Okay, all right, next equation. This guy. This is the same as what we usually write as displacement equals 1/2 at squared plus vit. Right? So here's my, let's highlight this so you can kind of see what's going on here. Here's vi times t, 1/2 at squared, 1/2 at squared. And then notice they've got x and x naught. Well, keep in mind, remember that delta x is x final minus x initial, right? By definition, okay? So if you think of this as x minus x naught, using our new notation, and then you add the x naught to both sides, then it gives you this guy, right? Cool? And I've just realized I've already been bad about my vector hats. Vector hats. All right, there you go, vector hats. All right? Okay, and then finally, this last equation. This guy here. So this vx squared is our v, oops. So this basically is vf squared equals v naught is vi squared plus 2a, here's my delta x, right? Oh, so this is vf squared minus vi squared equals 2a delta x, right? And don't forget those vector hats. Somewhere, somebody is watching this video who's not in my class right now and is cringing with my notation here. I recognize that this is a little bit sloppy. These are technically what are called dot products. So, there you go. All right, so at this point, the main thing that you need to be aware of is when you're looking at these equations, anytime it's got an arrow over it, that means you need to be conscious of your signs, your positives and negatives, okay? That is a very, very common issue. All right. So on your homework assignment, you're basically going to be refreshing your memory about these equations. We used these a ton in honors. I think the only thing that's new this year is this year we'll be doing problems like this with no numbers, which tends to be the thing that people get the most frustrated about in AP Physics. All right. So, sorry, I was seeing how much time I'd taken here. All right. So. Let me run through an example with no numbers, I guess before I do. Sorry, I forgot about this little page here. A couple other quick reminders. So remember, an object in free fall has an acceleration of gravity of negative 9.8 meters a second squared. The negative indicates down. I will very frequently use this constant, g equals 9.8 meters per second squared. Basically, that's going to be the main difference, all right, is that ag is negative 9.8 meters a second squared, whereas g is understood to be positive 9.8 meters per second squared, okay? So if I write negative g, that means negative 9.8, okay? We really will be using g more than ag this year, largely because that's what most colleges do, and I want you to get familiar with that notation, all right? On the AP test, weirdly, it's okay to use 10 instead of 9.8. Either on the multiple choice or even on the free response questions, all right? So that's definitely a huge time saver. I will, when I'm solving problems, I will use 9.8. If you want to use 10, please have at it. Just know that your answers will be slightly different because I solved mine using 9.8. All right, now, this is super important. Regardless of whether you use 9.8 or 10, please make sure you refer to G as what? What does G stand for? If you just said gravity, that's half of an answer. If you said force of gravity, that is wrong, because meters per second squared doesn't measure force. All right, this 9.8 meters per second squared, refer to G as the acceleration of gravity. All right, now we're getting warmer. Always? Is that always the acceleration of gravity? No, that is the acceleration of gravity near the Earth's surface. All right, and unless a problem says otherwise, you can always assume that this is where problems take place. But I just want to be clear. This is, G stands for the acceleration of gravity. All right, part of the reason that I use AG is because I like the fact that it has an A in there because it emphasizes that it's acceleration. The first year I ever taught physics, I used G, and people got confused between the difference between force of gravity and acceleration of gravity, and they kept wanting to call this force of gravity. It is not. That is the acceleration of gravity. All right? Okay, no numbers. What are we talking about? All right, so here we go. A ball of mass m is dropped from a cliff and it hits the ground after a time t total. In terms of t total and any physical constants, how long does it take to fall the first half of the distance to the ground? No numbers, right? Okay, so let's see if we can figure out what's going on here. So we've got a ball that's being dropped from a cliff. All right, it falls and it hits the ground after a time t total. Okay, so that's our time. And the question wants to know, in terms of that, how long does it take to fall the first half of the distance? All right, well, distance seems to be important here, right? Because that's what's separating the two things. All right, so this is a distance d, and this is a distance d over 2, right? So we want to figure out the time. So all right, so here's the trick. What we want to do is we want to pick an equation that has these variables. So we need to pick an equation that has d, you know, how far it falls. I probably could have called that displacement, right? And time. And then every other variable in it needs to be something we know. So what are the other things we know? Well, in both scenarios, I know that my, here, let me write it in red because this is true for both scenarios. I know that in both scenarios, my initial velocity is 0, and I know my acceleration is negative 9.8 meters a second squared. I'm going to not worry about the negative here. Let's make down be a positive direction here because the ball is always moving down. So we're going to call the acceleration positive 9.8. All right? And then we know our displacement. Oh, no. Okay, so how do we do this? Well, let's think about what equation do we know that uses these variables. What equation do we know that uses VI, acceleration, time, and distance? Well, the one that's jumping out to me right away is this guy. Right? And in both scenarios, this guy goes away, right? So let's see. And the question is asking us about time. So let's rearrange this using some algebra and solve it for time, right? So if I algebraify this, I'm going to multiply by 2, divide by a, and take the square root. So t is equal to 2 times our displacement divided by the acceleration, square root e, right? So what we know then is this. Oops. So what we know is this. T total is equal to 2 times d over a square root, right? And what we want to know is how long does it take to go half of that distance, right? So the square root of 2 times half of d over a, right? So the only difference is this 1/2, right? So this is the exact same thing as the square root of 1/2 times the square root of 2d over a, right? Oh, and look. T total is 2d over a. Oh. So this looks like we've got then t equals the square root of 1/2 times t total. Or, more simply, t total over the square root of 2. All right? So, there we go. No numbers. All right? There are a few of these on your homework. All right? Students struggle with these. The trick is, again, pick an equation that has the variables that are sort of discussed in the problem. In this case, the problem tells us about the distance it moves and the time it takes. And then you want to pick an equation that has the only other variables have to be variables you know, right? Like in this example, I don't know VF, so I didn't pick an equation that had VF. All right? I did know my acceleration. I did know my initial velocity. All right? So that's the deal.